Hello and welcome. We will end this series on videos on the induction generator used in wind turbines with a topic on the double fed induction generator and how we use that as an ideal concept for wind turbines. Once more, we start to explain that with the diagram of the rotor performance, where we see the rotor power depending on different wind speeds and also on different mechanical speeds of the rotor. And there we see, for example, when we have a fixed mechanical speed that is best for a wind speed of 7 meters per second, it's okay, but when we then have 8 meters per second, this speed would not be okay anymore. Then we would need a higher mechanical speed. For 9 even a more higher, and for 10 the highest mechanical speed. So to explain that more, what we lose when we operate with a fixed speed, we see here when we have a fixed operation speed ideal for 7 meters per second, we lose that pink part of power that we are not able to be transmitted to the grid when we are not using a variable concept. And that is what our double fed induction generator should do. So we once more see that we use the slip rings in order to influence our behavior of the rotor. And with an increased slip, that leads to an increased losses in the rotor that we have learned with the Highland circle. So instead of converting these losses just into heat in the rotor, it would be much better to feed this power to the grid too. But we can't do that because in the rotor we have a different frequency than 50 Hertz we need for the grid. And therefore in this concept we use a frequency converter to convert this current in the rotor to the 50 Hertz. And then with an additional transformer we adopt the right voltage level. And then we also can, in an over-synchronized operation with a higher mechanical speed than with the one is planned for the 7 meters per second here, improve the power transmission to the grid. And that we explain here with this Sankey diagram. So we start with the mechanical power transferred from the rotors, and then still the majority of the power, the largest fraction of the power, goes via the stator. But now due to this over-synchronized operation, we have an additional power that is fed through the rotor and through the frequency converter also to the grid. And apart from a few additional losses in the frequency converter, we have in total a higher power we are able to submit and transmit to the grid when we have higher wind speeds than the one with the fixed mechanical speed, when we are able to allow higher rotational speeds of the rotor. And that is the same when we go to a under-synchronized operation. It looks a bit more difficult and not so easy to understand, because what we see now when we have the mechanical power and the power submitted through the stator, there we see that a part of this power is fed backwards to the rotor circuit. And that seems to be a bit stupid, using power of the stator that is going redirected to the rotor circuit. But we need to understand that without adopting to a lower mechanical speed, the power transferred from the rotor blades would be much lower than in case we have now with this lower mechanical speed. And therefore it is completely okay that a part of this power is reversed through the rotor current, and in total again here we have a gain in power transmission. So finally we have an operation, or we have the possibility to operate the wind turbine always in the maximum operation point of our rotor blades. and therefore also have the maximum energy yield over the year when we have this double FET induction generator principle. And that's also the reason why nowadays with modern power electronics technology, most wind turbines sold and applied worldwide use this double FET induction generator principle. And with that outlook, I would like to stop this video series and thank you very much.